Hello everyone, I'm Khadija Kouchi. I recently graduated as a master's student in Chemical Engineer and Material Science at the Faculty of Sciences and Technologies of Settat. My presentation is entitled Solvay Synthesis of Nanoparticles Ni0.5Mg0.5Fe1.7Mn0.3O4 Iron Manganese Oxide as Anode Material for Lithium-Ion Batteries. As you know, lithium-ion batteries are an invention that has provided enormous benefits to society thanks to their high energy density, high operation voltage, and no memory effect. The initial challenge for lithium-ion batteries was to define a suitable cathode material facilitating the lithium intercalation-disintercalation. But actually, huge interests have been oriented to the development of an anode material meeting the requirements of high energy density and high safety. Since their development, the anode market has been dominated by graphite. However, the graphite suffers from its limited theoretical capacity of 372 mAh per gram, which barely satisfies the needs of large-scale applications. And to overcome these limitations, the development of some alternatives is required. Here, the transition metal oxide are a promotion class of material, especially the nickel magnesium iron manganese oxide. Our spinel-based material was synthesized using a Solvay method. Firstly, the following raw materials were mixed, then the citric acid that was used as a complexing agent was added into the solution. The mixture was stirred and heated up to 90 degrees C until the gel formation. The resultant residue was heated at 160 degrees C overnight and calcined at temperature between 250 and 800 degrees C. Now let's move to the characterization of our material. The X-ray diffraction pattern of the nickel magnesium iron manganese oxide material show us that the metal cations converge completely to pure spinel structure of the nickel magnesium iron manganese oxide material. The Raman spectroscopy was carried out to confirm the results of Xrd Analysis. The Raman spectra of our sample shows the presence of 6 vibration peaks, which could be attributed to the symmetric deformation, rotational and translational movements of the oxygen anion. Evaluated as anode material for lithium-ion batteries, the nickel magnesium iron manganese oxide displays interesting electrochemical performance. From the galvanostatic test and after 10 cycles, the electrode material can deliver a reversible capacities higher than 700 mAh per gram with a capacity retention of 83%. In order to understand the mechanism of this material, the voltammetry test was performed. These figures show us the cathodic and anodic peaks at 0.66 and 1.9 volts respectively. Generally, the iron triplus and manganese triplus goes to their metallic form during the discharge. The peaks at 0.66 volts could be also attributed to isoide formation. In addition, no large difference in the position of anodic and cathodic peaks was noticed, suggesting similar kinetics open charge discharge. More than that, the material exhibits excellent rate capability performance. Where the current rate has been increased to the highest value, specific discharge and charge capacities higher than 500 mAh per gram have been obtained. In order to improve the stability of the material, the carbon coating process was done under argon atmosphere at 600 degrees C using sucrose as the carbon source. This slide shows two figures, the first one without coating and the second one with coating. With coating, the material are more stable and the capacity retention was increased to 100%. So we can conclude that the carbon coating stabilizes the discharge charge capacities and give us excellent electrochemical performance. As a conclusion, this work consists of taking advantages from the electrochemical performance of the nanoparticles nickel magnesium iron manganese oxide and its use as anode material for lithium-ion batteries. So we have managed to obtain good electrochemical performance. Thank you for your attention.